Dear all, thank you to be virtually here. I'm Dr. Bucciarelli Alessio, and today I'm going to present a work that I have conducted on an inkjet printing process. So let me share my screen. So the work was conducted using a multivariable approach. Basically was done by considering more than one variable at time. First things first, let me briefly introduce where I come from. I'm part of the microsystem technology group that is inside Fondazione Bruno Kessler, that is a quite big research center in Trento. Trento is a small city enclosed in the Alps, as you can see by the mountain just behind the center. So we recently acquired Sera printer F-series, and we wanted to optimize the printing process. We had some constraint. We had to use Kapton as a substrate and a commercial ink from AGFA. Commercial ink based on the silver nanoparticle. We also had to use the Dmatics 1 picoliter cartridges. What we wanted to do was to increase the resolution of the printing process, basically decreasing the dimension of the single drop, and increasing the repeatability of the process by decreasing the standard deviation on the drop dimension among different process trial. So we could choose different approaches. One of them is the best guess approach that works reasonably well if we had some technical or theoretical knowledge on the system we are studying. However, it has two main disadvantages. The first one was that basically, if we are not having a good result by the initial guess, then we have to take another guess. And this could repeat forever. And the second main disadvantage is that there is no guarantee that the best solution has been found. So if we obtain an acceptable result, we are tempted to stop the testing, and we don't know actually if is the real best solution. Another possible approach is the one factor at time that is commonly used in literature, and it consists in selecting a starting point for all the factors that we are considering, and then varying one factor, maintaining the other factor constant. In this case, we do not consider the possible interaction between factors, and we do not consider the effect of these interactions on the interest properties. So we decided to use a statistical approach. This statistical approach comes from a field that is called design of experiment, and we decided to conduct a factorial experiment. In this experiment, we vary all the factors together. In this way, we can estimate the effect of each variable, but also the interaction between the variables. And we basically think about the inkjet process as a black box. Our system is the inkjet printing, and we had some controllable factors, and in our case, we decided to modify the waveform that we give to the piezoelectric. Then we had some uncontrollable factors that are noise that cannot be controlled, and this case is the ambient temperature, humidity, and the other environmental factors to make them not influencing the process, we conducted a randomized experiment. Then we have the response, that in this case is the printed pattern and the measurable properties of it. And we have some input. Our input is the material that we choose. So we decide to fix some factor, and we fix the cartridge head temperature to 45 degrees, the substrate temperature to 30 degrees, and the jetting frequency to 1000 Hertz. We basically decide to only modify the waveform of the piezoelectric to see its effects on the drop. So we modified the high voltage, the low voltage, and the time interval. We maintain the time interval equal for all the phases. Using the design of experiment, what we obtained after the data analysis is an equation that correlates our properties of interest to our factors, and these are first order terms, but also to the interaction between them. And this is the part that we are not going to see if we are using the other approaches. So we basically performed 3 trials for each of the 9 waveform, and for each trial we printed 400 dots. Then we performed an image analysis using ImageA. We masked the original high resolution image to obtain the to determine the contour of the dots, and then we calculate the area of the dots, the diameter, and the standard deviation on this dimension. We also calculated the circularity, and we also performed some measurement on the roughness. However, in this presentation, I'm going to present only the results on the area and its standard deviation. A first screening that has been done by an approach that is commonly used in data analysis is to produce a correlation matrix. The correlation index is an index that tells us if 2 variables are linearly correlated or not. We can consider a variable, 2 variables linearly correlated if this index is higher than 0.4 or lower than -0.4. So how we can see in the table, we had a strong correlation between the area of our splat and the high voltage and the low voltage, and we have a high correlation between the standard deviation on the area and the time interval. This is quite interesting because basically we can separate the area from the standard deviation if we watch just to the linear correlation. This doesn't happen if we consider the diameter, because the diameter is a derived measure that we actually calculate from the area. This is the results on the area. Basically, we can see that we can recognize from this graph some sort of pattern. This graph is called box plot, and it shows the distribution of the splat areas. We can see that there is some kind of pattern. A more accurate analysis can be conducted by using an ANOVA approach. And using the ANOVA, we can see which terms are significant on the area and on the standard deviation. The interesting thing is that, as we can expect it, the first order terms are basically all significant. However, we have also the significance of the mixed term. So we have that also the interaction between the waveform parameters are significant. And they are significant both in the splat area and in the standard deviation. So here is the final result, one of the final results. We derived the empirical model for the area, and here is the equation of the empirical model. We also derived the 95% high confidence interval and the 95% lower confidence interval, but we are not showing it in this presentation. So how we can see, to minimize the area, we have to squeeze our waveform. Basically, we have to decrease the high voltage and increase the low voltage. And the time interval doesn't have such a big impact on this minimization, as could be expected by seeing the correlation matrix, even though the time interval resulted to be significant from the statistical point of view. For the standard deviation, instead, the minimization has to be conducted by decreasing the time interval. This is the most important parameter. Then we minimize even further by decreasing the high voltage and increasing the low voltage. Also, in this case, we are showing the model equation, but we are not showing the 95% high and low confidence interval. To obtain an optimization on both parameters, we can choose different approaches. One of the most common approaches is to superimpose the two surfaces that we found, imposing some condition. So the best condition that we could find inside our variable space is with the high voltage on 25 volt, the low voltage at minus 5 volt, and the time interval at 4 microseconds. By the way, this kind of optimization gave us a sort of direction for a further optimization. In fact, we can think about extending this surface on the direction of the increasing of VL, decreasing of VH, and decreasing of the time interval. So, to conclude, we were able to find the best condition inside our variable space, and we could also determine a possible direction to further improve our results. We were able to find several factor interactions, not taken into consideration in the common optimization works, and not even in literature. These interactions were statistically relevant, and this is quite important. And I hope that I convinced you that design experiment in combination with data analysis are powerful approaches to characterize and control a process. Of course, we are going to conduct some more tests, including also the parameter that now we considered as fixed. So I would like to thank you all for your attention, and I hope that you have found this presentation interesting. So thank you.